Can you hear me well?
Maybe. Yeah, I think that's good enough.
All right, so I'll talk about the parity violation because that is the topic that has recently been reported in cosmology community. And then we have some interesting hint about the parity violation. And I'll also talk about my own work, this kind of old, 10 years old work, but then with the revival of parity violation, I think that will have much interesting implications. So I'll tell you about this as well. So there are three topics that I will talk today. Okay, good. So first one is something called the cosmic birefringence. That is using the CMB polarization power spectrum as an observable. We can probe the parity violation. And second is something called the galaxy 4-point correlation function, which is the lowest order statistic that is sensitive to parity. And so any higher order point function can work, but I'll tell you about the 4-point correlation function because that was reported recently. And my own work is something called the clustering fossils. So this will use a 2-point correlation function, but not in a conventional sense, but we'll use something called off-diagonal 2-point function. And you can add many more statistics. For example, if I use the semi-polarization to probe parity violation, you can also use the weak lensing field to compute the parity violation. And as I said, the higher order point function means the 5-point function, 6-point function if you are brave enough to measure them. Okay, let's get started with cosmic birefringence. So birefringence is a generic term referring to the fact that refractive index or the phase velocity of photon depends on the polarization. This phenomena was observed many times in the condensed matter. If you have some crystal-like structure, then if you have instant light here with the two naturally polarized light, and this is not unpolarized light, but then after it passed through the material, then this polarization and that polarization has different reflective index, so it will be dispersed. That's called the birefringence. So calcite is one of the materials that show this birefringence signature. That's why people show it here. So that I got it from this website, what's that? JeongRockAuctions.com. So this plot has a serious flaw. Can you see that? If instant light has 90-degree instant angle, there's no reflection, right? But it's good for this auction site. So we'll talk about the birefringence signal in the universe, and that birefringence signal is related to this epoch of the universe when the universe was about 380,000 years after the Big Bang. Then we had an epoch called the cosmic recombination, and immediately following the recombination, we do have the decoupling epoch for the CMB, cosmic microwave background photon, and then that photon will shows some signature about the birefringence. That's what I'll tell you about. So CMB photon is the recombination happens around 380,000 years after Big Bang. So universe is expanding. If you go back in time, then universe is contracting, and then temperature of photon is increasing and increasing. And then if you pass this epoch, temperature of universe of photon, average photon is 0.26 eV, or the temperature is 3,000 Kelvin. Beyond that point, any photon can break the hydrogen atom, so you don't have any neutral atom there, so that's called recombination. And then now let's move it forward. That means that after this epoch, you see the free CMB photons are not scattering and then freely traveling from the last scattering surface to us. And if you observe this photon, you get the full sky map is like this, right? This is a full sky map of CMB. For example, this is 1 millimeter wavelength. If you look at the CMB in the full sky, it's uniform. And you can also measure this CMB intensity as a function of frequency, and then you get the CMB spectrum. So this is a CMB spectrum measured over the past, I don't know, 4 decades, and including the Kobe Firas as the blue, and then rotation excitation mode, and then ground space telescopes, and then balloon, and all those things. And you can compare this spectrum with a Planck curve with 4 Kelvin here as a pink, and then 2 Kelvin as a yellow. And then This mass splitting curve is green, that is the 2.725 Kelvin blackbody curve. So by observing the CMB at many different frequencies, we know that CMB follows a blackbody curve with temperature this precise, 2.726 plus minus 0.0013 Kelvin. Okay. Of course, we can also parameterize the deviation from this blackbody, that we normally use the Compton Y parameter or the mu parameter as of the chemical potential in Bose-Einstein distribution function. And those two numbers are constrained to be less than 1 part in 10 to 5 and 1 part in 10 to 4, respectively. This is remarkably blackbody. But if you increase the contrast of this map, so Y is a conventional way of parameterizing the deviation from blackbody when the CMB photon is passing through the galaxy cluster. It's called the Compton Y parameter. That's why we call it Y. And mu, so there's some physics here. So if you inject some energy to CMB photon after redshift 2 million, that redshift 2 million marks the important epoch in the universe. Before redshift 2 million, we had photon creating processes like double Compton scattering or Bremsstrahlung and double Compton scattering is very efficient. But after redshift 2 million, then we don't have photon creating process anymore. Okay? Which means that if you inject some energy to photon, then you can increase the energy, mean energy of thermal bath, but you're not allowed to create more photons, right? But then if you think about the blackbody has only one parameter, which is temperature, right? And then blackbody at different temperature have definite relationship between the energy and density. Now you violate that definite relationship. Yet, CMB photon at that high redshift 2 million, is scattering frequent enough to resort itself to another equilibrium state. And that equilibrium state can be described by Bose-Einstein distribution function. And then that distribution function has two parameters now, temperature and mu. That's why we describe it as mu. So this mu and y are two different ways of describing the deviation from the blackbody. Good? So if you increase the contrast of this map, now you see this famous map of the temperature and entropy in the universe. So this is also a full sky map. This is measured from the Planck satellite. This is something called the maximum likelihood posterior map. Means that in the middle of this map, where we have strong galactic emission, that is just our imagination. Okay? But this map, we use this map for the public outreach or just to explain people. And then same map, we can also put a polarization map of CMB. Here, the large scale color coding is the smoothest CMB temperature. It's a hot spot and a cold spot. And then line here correspond to the polarization of CMB. Polarization of CMB means that at each direction in the sky, we put the polarizer and then measure the direction of polarization of the E field of the CMB. Then at each point, we can throw a line here, right? So line here is a representation of spin 2 field. So CMB polarization field is also spin 2 field. So why should CMB be polarized and then linearly polarized? This physics is very well explained in this website by Wayne Hu. So if you have instant photon here on polarized light and scattering through some medium, and then you see the polarization. Okay, that's the physics, and that's all. So if you have this electron here, sitting here, and then we see the unpolarized light coming from the left to right, and you're observing this photon here, and then you see there are two different modes, but then only this polarization, this mode of polarization can generate the light, the outgoing light in this direction. You only see this polarization. And you can do the same thing. Consider these two directions as the direction of photon at the last scattering surface. And then there's a photon scattered through this electron and then coming toward us. Okay? Then if you think about these two photons with same intensity, there's no net polarization. Okay? If you have same intensity, and there's no net polarization. But if you have the two polarization, incident light from the left has much stronger intensity than coming from up, then the net polarization is parallel to the direction of this blue, right? That is why CMB must be polarized. And then you can see that polarization of CMB must be very strongly correlated with the temperature structure on the free electron at the large scattering surface. That was indeed the case, which is shown here. This is a patch of the sky map observed by Planck. And then we see that there's some consistent pattern here around the hot spot and cold spot, but it's kind of hard to see. So what people did in Planck team is in this paper, Planck 2018 paper, what they did was they stacked the polarization pattern around the hot spot. So you pick up the hot spot and then stack the polarization around the hot spot for the entire sky, and that's what they get. Center, we have hot, and then decrease, and then cold, and then hot, and then you see this red ring, which is hot spot, has polarization pattern, which is radial, and this one is magenta purple, which is cold spot, and has a tangential polarization pattern, which is of course what you expect from the simulation, right? Okay, so that's that. And then because this polarization is spin-2 field, we can decompose it by parity even part and parity odd part, if you do that. And this is a map, artificially created polarization map from the Kamyankowski and Colbert's review paper. They generate only E mode polarization and only B mode polarization. E mode polarization is acronym for the parity even part, and B mode polarization is acronym for parity odd part. Parity even part and parity odd part, because this blue is the negative E mode and red is positive E mode. If you place the mirror here and then deflect this image, you get it goes to itself, right? And then this one is also goes to itself. It doesn't change the sign. And this here, the blue is negative B mode and red is positive B mode. If you place the mirror here and then reflect, and the negative E mode goes to positive E mode, and positive E mode equals to negative E mode. It's the flipped parity. Okay. And B mode and E mode decomposition is very important in cosmology, because among all the early universe physics, parity even part or E mode polarization can be generated by all of them. Scalar can generate E mode, vector can generate E mode, and tensor can generate E mode. On the other hand, scalar perturbation from the inflation cannot generate the B mode polarization. Okay, so B mode can be only generated by vector or tensor mode. That's why we are so interested in decomposing these two modes, and then we measure separately E mode and B mode. So far, we have been measuring E mode casually. We measured the B mode on the small angular scale, but those B modes are not from the primordial universe. That those B modes are from the E mode that was gravitationally lent toward the B mode. So that's the difference. So we are still chasing after the primordial B mode signature, which can be a smoking gun signal for the cosmic inflation. All right. So how do we use this E mode and B mode to see the cosmic birefringence signal? The cosmic birefringence signal was studied. It's a very long history. It started from the 70s, and we have papers 80 and 90 and 91, 92. Okay. The origin is this Lagrangian. So if you have the photon field and have some actual action field and coupled with this manner, so some coupling GA times theta, which is the pseudo-scalar field, and F is our beloved photon field, and F dual. F dual is pseudo-scalar, so if you multiply pseudo-scalar, then it will be a scalar. So that's a perfect candidate for the term in the Lagrangian. And this is a form of Chern-Simon interaction term, which in general can be written as P mu A nu and F tilde mu nu. If you do the integration by part, you can convince yourself that you can just put one derivative in F into theta, and then this partial mu of theta can be something like P mu. That's why I call this Chern-Simon's term. I think you'll hear more about the axiom from Professor John's talk from tomorrow, but just brief introduction about the axiom. The axiom is a pseudo-scalar field introduced by Patchy and Quinn in 77 to explain the strong CP problem. Strong CP problem is not the CP is so strong, as the name suggests. They might suggest. The strong CP problem means that the question is why CP is not violated in the strong interaction. Okay. So they introduced some dynamical solution using the action. That was the origin of that. Yoongjin can tell you more about it tomorrow. And for those who are not familiar with this notation, F mu and F mu nu, and this is a fancy way of writing down Maxwell's equation using field strength tensor. F mu nu is defined by partial mu a nu minus partial nu a mu. Okay, and F mu nu has this component, and then F upper mu nu has this component, and F tilde mu nu has this component. But what you need to know is like F mu nu times F mu nu, which is the B squared minus E squared, which is a complete scalar. But F mu nu times F tilde mu nu is nothing but B dot E. So if you do the parity transformation, this B dot E will change its sign. That's why it's called a pseudoscalar. Okay? So let's proceed with this Lagrangian. And what you can do is, that's what I did. So what you can do is we can do the one integration by part, because Lagrangian density only makes sense instead of integral. You can always do the integration by part. And then what's left after pulling out the total derivative term is this term, A mu times F mu nu times this one. And then you can interpret this as if we have some extra current. Okay, so you have A mu here, and then you can read off this whole thing as J nu. And then you can rewrite the Maxwell's equation like this. So here, if you set GA to be 0, then you go back to our old Maxwell's equation. But because of this Chern-Simon type interaction, we have this one proportional to the gradient of action field, and this term proportional to the time derivative of the action field, and then gradient of action field. Okay, so you can immediately see that constant action field will not do anything. If action field changes time or vary in space, then it will do something for us. Okay, and then now that you have this E field and B field, then you can also write the wave equations. Oh, yeah. And of course, if you have GA 0, then we have 0 and 0 that has usual electromagnetic wave propagation equation. But because of this Chern-Simon interaction, then we have GA times this and that, again, depending on the derivative of action field. And then if you solve the dispersion relation by assuming that action coupling is small and action varies much, much slower than E field and B field, which means that we essentially neglect the gradient of action, then you get the dispersion relation, which is different for the right-handed photon and then left-handed photon. The photon has two polarization modes, right-handed and left-handed. What it says is that they are propagating with different speed. Okay? That's why we call this cosmic birefringence. So the positive, negative, plus, minus means the right and left-handed polarization mode. They're propagating with different speed, right? And then the speed difference is 1/2 of action coupling times theta prime. Okay. Here I cheated a little bit because I solved it in the flat Minkowski space, but then now I call this prime as conformal time derivative. I can do this because photon fields are conformally invariant. So whenever you solve it for the FRW universe, what you can do is you do it for the flat Minkowski space and then just change your time to conformal time. And then you get the valid equation here. All right. So to summarize, this type of new interaction term will give rise to parity breaking signal. Here, parity breaking means that left-handed photon and right-handed photon has some different physical characteristic, which is a different dispersion relationship. That means that if left-handed, and then you can think of the linear polarization, which is relevant for the cosmological setting because all the CMB photons are linearly polarized because of the quadrupole that existed at the decoupling last scattering surface. So linear polarization can be written always as a superposition of right-handed and left-handed photon. But then if right-handed and left-handed photon are moving at different speed, and as a result, linear polarization will rotate. Okay? And then this rotation angle is given by 1/2 times GA, the coupling times integration of the eta, the conformal time, times theta prime. This you can integrate, right? That's a theta at the last scattering surface and theta right now. So rotation angle that we observe from the CMB analysis is exactly the difference between the axion field value at the last scattering surface and now. So that's what we are trying to find. So last scattering surface, we have purely E-mode polarization pattern here and there. Okay. Then during the propagation of this light, let's say our universe is filled with action, and this action is dynamical. That's important, right? Because we are looking at the difference of the action field value at the last scattering surface and present time. If action is dynamical and can induce the shift, the angular shift amount is 1/2 of GA times action field difference. Then if you have this purely tangential mode, rotating everything with a constant angle will give rise some swirling-like pattern that we call this B mode. And here as well, purely radial mode can show now some curve type mode that we call B mode. Okay. In the equation level, if you have E and B mode in the primordial universe and how does that appear in the observed plane, this is the equation. So EE, PB, EB there, those are the primordial correlation function of E mode and B mode and EB cross correlation. And then observed EB cross correlation is now related to the primordial value times some beta, right? This beta is the angle that is the shifted angle caused by the axion photon coupling. Right. We normally assume that primordial universe doesn't have EB cross correlation. That means that the observed EB cross correlation will be a smoking gun signal for measuring this sine times 4 beta. Okay. People has been measuring this thing for a long time. Even WMAP first year paper, they tried this thing, but then the sensitivity was so low, and then they just reported that as a systematic check of if the instrument that we have, the WMAP, is rotated, it has some rotation that we didn't know. But then the great advance has been made after the Planck, because WMAP and the Planck, those are two completely independent satellites. There's no reason that the instrumentation rotation of WMAP is correlated with the instrumentation rotation of Planck. So this rotational, they can measure and then they can subtract. Okay, and then that's what this paper has done in Astin and Komatsu paper. So they measure the EB cross correlation, which is black, and then this red is something called the miscalibration angle. That is the rotation of instrument that we didn't know, which is very well under control because they can measure this from the dust foreground. The dust. We'd expect that dust will emit some polarized light, and using the dust, they can calibrate both Planck and WMAP and use the fact that they are independent. And then this blue line is a cosmic birefringence signal, and then the best fit value, the combining those two are this. And then from this measurement, they measure the beta, the rotation angle of 0.34 degree plus minus 0.09 degree, which is a 3.6 sigma detection. That's very interesting. And then here, what you can claim is that we see the rotation of the CMB polarization. We do observe the one rotation angle, but then how are we sure that this one is cosmic birefringence? Of course, we are not sure, but they excluded one other possibility, which is called the Faraday rotation. If the line of sight, if there's a line of sight direction of magnetic field, right, from the last scattering surface and us, and this magnetic field can continuously rotate the the polarization of CMB as well. That is called the Faraday rotation. But then Faraday rotation prediction is n of -2. We expect to have stronger frequency dependence with the Faraday rotation. But then when they use the 7 channels, 1, 2, 3, 4, 7 channels that we observe, the CMB fluctuation, this observed birefringence angle does not show any strong new dependence. So we think that this is consistent with the birefringence. At least it's not due to the magnetic field effect. Okay? And what are the other options? So my colleagues and I, we try to explain this signal with some dark sector physics. I think here my colleagues are sitting there. And in this paper, we try to explain this birefringence with some unknown birefringence that we might have in the dark sector that is propagated through our sector using the kinetic coupling. Okay. In this case, the observed birefringence is proportional to some epsilon that is kinetic coupling, and then square root of intensity ratio times the birefringence angle in the dark sector. Okay, that we saw this great, and then we can explain at least the frequency independence, because as long as dark photon temperature is lower than the CMB temperature, then we are both looking at the Rayleigh-Jeans regime, and this intensity ratio stays constant. So we can explain the new independence, but there's a bigger problem for this model to explain the observed mean signature of birefringence, because if you had a dark photon which recombined in the early universe, this dark photon recombination must happen early on. Otherwise, you would observe this effect in our galaxy power spectrum. And the polarization angle, the linear polarization angle of dark photon is fairly independent of linear polarization angle of our photon. So there is this one parameter that describes this the polarization difference that is essentially random, and that signal erases all the mean signal. So I think we can probe this effect. If this effect exists, we can look at this effect in the 4-point function like EE, BB trispectrum or spectral distortion, but cannot generate the mean signal that we observed. That was unfortunate, but this conclusion is fairly generic. So we are not, at least we are not looking at the dark birefringence reflected onto our birefringence using this kinetic coupling. Any question? This is it for the birefringence. Okay, 3.6 sigma. That's the bottom line, which is fairly interesting. But bad news is that we already used up L of 100 to L of 1500. How can you improve upon that? That's an interesting question. And then, yeah, I don't know. I can.
Model and axial model are different models, right?
Yeah, it's different model. Yes. So here, axion, they assume like there's axion coupled to our photon, and dark photon model is that axion is somewhere else in dark sector and coupled to our photon using the kinetic coupling. Right, and then there's one mission that we have in Horizon is something called the Lightbird. That's Japanese mission, the satellite base. That will make the measurement of CL, BB, and EE less than L of 100. But then, yeah, they might have some detection, but then, I mean, just counting number of mode, L less than 100 is not that much compared to L between 100 to 1500. So I don't think this I mean, it's hard to improve upon this 3.6 sigma unless we have something very spectacular in two decades from now. Okay, let's move on. I'll go to the 4-point correlation function. So cosmologists love correlation function because that's the one thing that we can measure and then compare that with the theory. Okay. So lowest sort of correlation function that we are using is something called 2-point correlation function. Okay. As defined, is C is defined as excess number of pairs, galaxy pairs or matter pairs beyond the random as separation R. Means that this is one snapshot of simulated galaxies, and we choose one galaxy okay, and count number of neighboring galaxies as a function of R, and compare these pair countings with the expected value that if there's no correlation. Okay? And in terms of math, we use the delta. Delta is the density contrast, which is the measured density at this position over the mean density and -1. That's why it's constant contrast. If you average this delta, you get 0. And then in terms of delta, C is given as delta square, delta of x and delta of x plus r. That's why we call this two-point correlation function. Okay, the two-point correlation function geometrically is a line. As a function of r, line, you can compute the number of neighbors. You can go one step further, you can define the three-point correlation function. Three-point correlation function is what's that? Zeta. That's excess number of triples beyond the random at separation r and s. You start from one galaxy, measure the neighboring galaxy as a function of distance r and s. Okay, and then compare that with the expected number of triplets in the completely random universe. In terms of delta, you have delta of x, x plus r, x plus s. Okay? And then this three-point function is represented as two lines, or if you want, you can just close the line and make a triangle. Right, now let's think about the parity inversion of these two geometrical objects. You have 2 points. Okay, we reflect that in the mirror. You have this image. That should be exact because I just draw this thing in the keynote and ask keynote to flip. And of course, if you start from, if you're looking at this 2 point and these 2 points, what you can do is drag these 2 points off the plane and then come back. It means that you can rotate. You can start from here in the left image and rotate that to go to the right-hand image. Right? The two-point function, even though you flip the parity, you can always use a rotation to go to the parity flipped universe. Okay? Good. So it is not sensitive to parity. Three-point function. We have triangle. Parity flip. Of course, you can also drag this image to make the exact match. Again, three-point function. If you do the parity flip, you can always rotate to go to this triangle. So they are not sensitive to parity. What about the four-point function? I mean, I don't bother to write the same slides for four-point function, but you should know that four-point function is a count of 4 galaxies beyond random, right? 4 galaxies can be always put into the points of tetrahedron. You have this tetrahedron, R1, R2, R3. Flip the parity, you go there. If you have this tetrahedron, try to rotate. Oops, you don't get this, right? That's why four-point function is a lowest order correlation function that is sensitive to parity. Okay. In fact, if you have 3 vectors, R1, R2, R3, you can combine them to have the pseudo-scalar R1 dot R2 cross R3, which cares about parity. That's what people measure. So what people did is they went to Sloan Sky Survey and found all possible 4 galaxies within some radial beam, and then they count number of left-hand, I'll say this is left-handed without no justification, and right-handed. How many galaxies we have? Left-handed tetrahedron or right-handed tetrahedron? Okay? There are 2 measurements. So first reported measurement was from the group in the Florida, Jamin and Jacques Slapian and Robert, and they claimed that from the C-mass galaxies, from the both sample, they detect parity of 4-point correlation function at 7.1 sigma. That's great. And then second paper came out from Oliver Wilcox. He used to be at Princeton, but he's now at CCA, the Flatiron Institute. And he said with the rank test, give a detection probability of 2.9 sigma. Well, a little reduced, but you have to understand that the quantifying the uncertainty for this measurement is extremely hard. So I was encouraged to see that they both get something more than 2 sigma. Okay, that was the status. In the galaxy, there seemed to be some signal of parity violation. We seem to have more one side of tetrahedron than the other side of tetrahedron. That was reported end of last year. And this is still very hot. And the same author, Oliver, he went on and to measure the trispectrum of CMB, because if trispectrum is the lowest order statistics sensitive to parity, why don't you look at the CMB, right? And then he said, that's the conclusion. If we found consistency at the 0.5 sigma level, yielding no evidence for parity violation with roughly 250 times that's the mode counting. So no evidence in CMB. It's getting more interesting, right? If people were given this result that galaxies seem to care about parity, and then our natural starting point is, inflation might generate something in the early universe that is violating parity, right? But then his conclusion is, and he also even tested, what is that? Constrained physics models of inflationary parity violation, including ghost inflation, cosmological collider scenarios, and Chern-Simon gauge field. And these results suggest that the recent parity excess seen in the Bose galaxy survey are not primordial in origin. Maybe that's too strong statement, because you can still have some parity violation in the primordial universe that is somehow hidden in the CMB, right? CMB is observing photons, right? I mean, you may have something hidden in the dark matter, which we didn't see in CMB. So but still that's interesting. I mean, the requirement is that if you have some parity violating physics, then we have to be able to hide it from the CMB. That's the status that we have so far. Okay. Then that gives rise to some new perspective of my old work that is called the clustering fossil. That is another way of looking at the parity violation. That's why I brought up here. And I go back to these slides, the Dirac delta and homogeneity. If you look at this equation, we cross-correlate density contrast and X and X plus R. But then this product, F the ensemble average, this one is not depending on X at all. That is a statement of statistical homogeneity, means that no matter which galaxy you start from to compute this 2-point correlation function, you must get the same answer. Universe is translationally invariant, okay? And that statement is related to the Dirac delta function, the Dirac delta operator, sorry, in the Fourier space. Yeah, here my student is sitting there. Whenever they say Dirac delta function, I said, no, it's not a function. So I should be careful. Okay, Dirac delta operator. So this Dirac delta is a signal for the statistical homogeneity. What if statistical homogeneity was broken? How can you quantify this thing? And the way that we can quantify this is using the non-Dirac delta function, right? It means that if you have two density contrast, delta of K1 and delta of K2, if they are non-zero, even though K1 plus K2 is non-zero, right? Now I'm doing the complementary operation of this operator. Then that can be a signature of statistical inhomogeneity. Okay, means that statistically this part of universe is different from that part of universe, different from that part of universe, right? But then let's say we want to quantify this statistical inhomogeneity. How do you do it? What I would do is define this K vector that is minus K1 plus K2, means that how much is K plus K2 deviate from 0. And then most generally, I can write down this 2-point correlation function, which has a homogeneous part and inhomogeneous part with this Dirac delta. The Dirac delta here is there just to show that there's some organized way to quantify inhomogeneities. Okay, this is very similar to the case for the anisotropy, and I show you this example because this is very illustrative of what I'm trying to do. So when you quantify the anisotropy of the CMB map, what you do is we use something called the bipolar spherical harmonics, or BiPosh. Okay, we have 2-point correlation function of ALM, AL prime, M prime. The leading part is this diagonal part. Then we do have off diagonal part with a coefficient big A, J, M, L, L prime. Here J is a total angular momentum that you can construct with L and L prime. And M is a total magnetic angular momentum from M and M prime. This one, this little symbol is what you saw in quantum mechanics or Jackson. It's called the Gordon coefficient. Okay, so it means that this M and M prime must give M minus M prime must be M, right? And then there's Wigner 3J and 6J, all those things. So this is one example. So here is the map of CMB sky if we were moving to direct north with speed of light. It's not our universe, but I just want to make the example. So if our motion with respect to CMB rest frame is about 1, then that is the CMB that we'll observe. The effect is very easy to understand. This is all about the relativistic beaming effect or the aberration effect. In the forward direction, hot and cold spots are getting smaller and smaller and smaller. And the backward direction and the hot and cold spot in CMB, they're getting bigger and bigger. By looking at this, we can immediately say that, oh, there's something happened to enhance the clustering here and then reduce the clustering there. And this change that we can call anisotropy, and that the pattern of anisotropy has dipole. The dipolar pattern of anisotropy, and this dipole is aligned to the North Pole, which means that this BiPosh coefficient is predominantly A10. Okay. That's what I want to do. So what you want to do is that you can measure, we want to measure the degree of inhomogeneity. We don't just want to measure that, we want to measure how this degree of inhomogeneity appear in the sky in the coherent manner. Okay? That's why we introduced this big K. Then why am I bothering considering this inhomogeneities, right? First of all, that can be a good test of systematics, right? If I have a galaxy survey, and then if there's some unknown systematics that varies over the sky, right, then I should see that as a signature of the octagonal correlation. Or our universe might be intrinsically inhomogeneous. I mean, the statement of statistical homogeneity and isotropy is the thing that we hope, because that is kind of only way we can write down the good basis for the analysis, right? But then our universe doesn't necessarily follow our convenience. So it's still possible, although the allowed parameter space is quite narrow. And third one is if you have some higher order non-Gaussian correlation function of some nonlinear field to the density field in the universe, in the all universe, then this higher order correlation function appears to give us the clustering, the signal, off-diagonal clustering signal. That's called clustering fossil. Okay, so that is the idea behind my 2012 paper with Mark Kamyankowski. So we start to use this equation for the breaking of the local inhomogeneity. If we have nonlinear coupling between primordial density field and some spectator field, HP, so some spectator field with any spin. This 3-point function of density, and this spectator field, okay? Most generally, we can write this interaction 3-point function as proportional to P of P, because if you have higher amplitude of spectator field, we do have stronger amplitude of coupling, and then this coupling amplitude and polarization basis, epsilon ij times k1i, k2j, and then we do have Dirac delta here because we do not break the global homogeneity here, right? And this 3-point function can be translated into this conditional 2-point function. Conditional means that in the presence of this HP field of wave number k, we do expect to have delta density field of ki, density field of kj. I here means initial, as predominantly, first of all, we do have a diagonal component, and then we do have off diagonal component, that is proportional to the amplitude of this spectator field. Okay. So why do we call this sort of fossil? So inflation is, in Platon, is some scalar field responsible for inflation, but in Platon may not be alone, right? There might be some other field, like other scalar field or other tensor field and other vector field. Scalar field, if there's other fields, the scalar field amplitude is constrained by isocurvature mode. It cannot contribute more than certain % of the density perturbation. And vector field is even worse. Vector field decays as 1 over scale factor regardless of the scale. Inside horizon, outside horizon, they all decay. Okay? And tensor field, it stays constant outside the horizon, but after the horizon entry, tensor field decays too. So these vector field and tensor field most likely are not here today to be observed. But if they couple to the inflation, the curvature perturbation early on, that coupling is still remained in this off-diagonal correlation, and we don't have any other physics that can generate this off-diagonal correlation later on, that means we can study those existence of these fields, these spectator fields, spectator vector and tensor field early universe by using this off-diagonal correlation. It's like we don't have dinosaurs around us, but we can still study dinosaurs by looking at their bones and then footprints, right? That's why I call clustering fossil. And clustering fossil that contains a lot of information because of this polarization tensor. Polarization tensor can be decomposed by scalar mode and vector mode and tensor mode. It's like if you learn the relativistic perturbation theory, you can decompose the spatial part of your metric perturbation, which has 6 components, symmetric spin 2, symmetric 2 by 2 matrix in 3D. And you can decompose it by 2 scalar mode and 2 vector mode and 2 tensor mode. And depending on this characteristic, it has characteristic shape of the polarization tensor. That is the key. And then because of, depending on this polarization tensor, it changes how this spectator field must couple to the density perturbation, okay? And then this angular dependence is shown here, and then they can generate the pattern, angular pattern of which this 2-point correlation function changes. So I will show you some examples. So if you have scalar mode, we call H0, going from the bottom to top, the propagating scalar mode that can affect the density perturbation, can generate the coherent change in the equal correlation function surface. It has one complete circle, and then it will shrink the volume and expand the volume. That's what the scalar field does. Scalar mode does if it's proportional to delta ij. That's all that it can do. And if it's longitudinal scalar mode, it will elongate one direction and then squeeze the other direction while keeping the volume the constant. That's what it is. For vector mode, we have hx vector and hy vector. It'll make the change in the perpendicular direction, like this xy section. And for tensor mode, it will make the change like in the spin 2 kind of change, like cosine 2 phi dependencies. But because now we have tensor and vector field with x and y, and then plus and cross polarization, what you can do is construct a helicity basis. For vector, I can, instead of having eijx, eijy, I can have eij plus minus v and eij plus minus t. Same for tensor, which means what I can do is I can also measure right-handed vector and left-handed vector, how they couple with the scalar mode. By comparing the power spectrum amplitude of the plus mode and minus mode, we can test the parity. Okay? That's the third way that I can think of that you can measure the parity violation. So I'll show you one example, starting from famous Maldasson's calculation in 2003. What he did was he computed in this paper that, he computed like various 3-point functions like delta, 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 and delta HH, but one of them is zeta, zeta, H. So it means that scalar tensor cross correlation. And that has this lengthy formula, but in the squeeze limit, where the tensor amplitude, tensor wavelength is much longer than the other 2 scalar wavelengths, this formula reduced to this form. Indeed, this is proportional to power spectrum zeta and power spectrum spectator field and this polarization tensor, just like what I wrote as JK coupling. So you might think that, okay, that's it. Let's just plug this into the formula and then get something out of this. That's not the way, because if you use this formula as it is, there seems to be some super horizon mode affecting our observation, which is impossible. So we have to kill that. And on the other hand, also, we do have direct coupling between the tensor and scalar right around the moment of the horizon entry of the tensor perturbation. Okay, the tensor perturbation, while it's staying outside the horizon, by definition of outside horizon, we should not be affected by the tensor mode at all. But right around the time that this tensor mode re-enter the horizon, what it does is it will generate slight amount of anisotropy in the universe, right? And then the evolution of this scalar mode must fill this anisotropy. And this is a paper that I wrote with Liang Dai in 2013. And when in the case that the wave number of tensor mode and eta is a conformal time, so one means that this tensor mode enters the horizon here, and then this amplitude of coupling between the tensor mode and second order density field increases and then oscillate, and to get the asymptote value of 0.6, 3/5. And that's the direct coupling, the physical coupling between the tensor mode and the density field. But this does not kill the super horizon mode yet. To completely remove the super horizon mode, we have to take into account the light deflection effect. So light deflection effect is following. So let's say we have galaxy here, and then this galaxy is shining in the universe only filled with gravitational wave. To simplify the situation, the light path of the light emitted from the galaxy is bented because of metric perturbation, right? And then it bented here, and then we observe, as an observer, we observe it to the direction n in the sky. What we do is we chart this galaxy, not here, because there's no way that we know what light did for this galaxy. Instead, we chart this galaxy based on the observed redshift and then sky location to here. And there's a coherent and systematic difference between the original location of galaxy and then the location that galaxy is charted to, right? And that deviation is proportional to the metric perturbation in this simple universe where we only have the metric perturbation Hij, and that delta x is given by -1/2 of Hij. So including everything, now finally I can relate the primordial coupling that Maldacena computed and then coupling that we would observe in this universe. So this is the amplitude, so that's the quadrupole power spectrum, means that when you take the k goes to 0 limit, that's the limiting value. This is if you just use the Maldacena's computation, the primordial signature, then we expect that this mode, this amplitude, this contribution of each k mode. But then this is wrong because obviously because we do have contribution from the super horizon mode. That's not allowed. If you include this nonlinear coupling, then this will decrease the influence of the mode smaller than the current horizon side. This is the current horizon side. But then we still have the amplitude, some amplitude remained from the k of 10 to -5, which is insane. Only after we include this projection effect, the light deflection effect, we do have this solid line, which means that now we don't have any super horizon influence, right? So that finally makes sense. So that's the story from this one example case that it comes with the plain vanilla inflation model with single field slow roll. Of course, this fossils doesn't have to be, inflation doesn't have to be slow roll single field, right? And then we also computed the same effect from the solid inflation and then quasi single field inflation. All those things contain the scalar tensor coupling beyond the single field slow roll inflation model. For those models, this signal can be big. And that gives at least me the motivation to go out and measure this signal from the galaxy surveys. So how do we measure that? So that is the equation that we started from, the fossil equation. In the presence of HP, we do expect to have delta of K1, delta of K2 couple in this particular way. And if you are to measure HP, the amplitude of primordial spectator field, what you can do is for given HP's K mode, we can attach two delta, K1 and K2, and K1 and K2, and K1 and K2. And you can add them, all the pairs that give rise to this sum of K, and then divide by this coupling, right? That's it. Depending on the spin of the spectator field, we weight these different pairs differently. Epsilon ijp, ki, k2, k1i, k2j. And the most important difference is azimuthal angle difference, okay? So for spin 1 field, we multiply cosine phi. Spin 2 field, we multiply cosine 2 phi. Spin 3 field, we multiply cosine 3 phi. Spin 10 field, we multiply cosine 10 phi. It's a generic way of figuring out the spectator field with higher spin as well. I mean, of course, we know that there's a theorem due to Weinberg and Witten, but we have open-minded for the early universe theory, right? There might be some higher spin field that exists in the early universe that might couple to scalar field. Then this signal should show up. Okay. And then in this paper, we went out to compute what's the optimal way of combining this K1 and K2, and we did this equation and got this result. Okay. Yeah, these are the 10 gigaparsec scale survey like Sloan's Sky survey, and these are 200 gigaparsec like survey like SKA or DESI or Euclid or SpearX, right? To observe this kind of signal from the single field slow roll inflation, we have to go out to K of say 3, which sounds insane if you know the status of art of galaxy survey analysis. But if you go to higher and higher redshift, and these K mode might be accessible. Also, we do not know any other low redshift physics that can generate this cosine 2 phi, 3 phi, 4 phi. Okay, so I think this area of off-diagonal correlation function is quite intact. So we might have some chance to observe this signal from the galaxy surveys by looking at the off-diagonal correlation function. All right, let me conclude here. Summary, so from the cosmic birefringence, we do have 3.6 sigma hint. And from the CMAS galaxies 4-point correlation function, we do have, depending on who you ask, between 7.1 sigma to 2.9 sigma hint for the parity violation. Okay, and then we don't have evidence from the CMB trispectrum. And then I think if you are to pursue this direction and then chasing after parity, clustering fossil could be a way to look for the signature from the parity violation. And it can also tell us something about higher spin field and the parity. Thank you.